Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
All right, I guess we could start. So let me thank to Yuval for finding time to stop by and giving the talk. So it's much appreciated. I guess it's a very old subject, but still with new and interesting results. So bandits with switching costs, please.
Good afternoon. It's a pleasure to be here. So this will be the bandits here referred to the multi-armed bandits, the kind of machines in casinos where you pull an arm and hope to get a reward. And they differ from other formats of online learning because of the type of feedback that you get each time. That is, you find out what happened from your action, but not what would have happened had you done another action. This is joint work with Ofer Deckel from MSR, who introduced me to this subject, Jian Ding, now at the University of Chicago, and Tomer Koren, who was an intern with us from the Technion. So I know we have a mix of some experts and some newer to the subject, so I'll have to go through some background, getting to the main point. So we're going to discuss online learning with k possible actions. It's often called also the learning from experts problem, where you have experts proposing to you several actions, and you have to choose each time what to do. So you have the player or the learner, and he has to choose each time between k actions. Mostly, we'll think of k as a small constant and focus on 2, but everything applies when k is a bit larger as well. So these are the actions the learner can choose. He can choose whether to buy stock A or buy stock B, or maybe he can choose which route to drive or which route to send his packet each time. And a priori, he maybe doesn't know how well the different options will perform, but he learns over time. And this type of problem is considered in kind of a Bayesian setting with some distribution over the environment, and in a worst case setting where the player wants to see how he does compared to maybe sticking to the advice of one of the experts or one of the actions. So we'll consider an adversary, which is a priori could be a worst case. So each time the player chooses an action and receives a reward or a loss, so we'll think of these as losses. So the cost of doing the action, of course, you can shift by constant and think of this as a reward. So each time he makes such a choice, he gets the reward, and this goes on over time. And well, the problem is what should he do? And we'll see several different settings depending on how powerful the adversary is and what kind of feedback the player gets in each round. So in order to deal with a worst case adversary, it turns out important for the player to be able to randomize, because if he goes according to some deterministic strategy, then there is a worst case adversary who would exploit this strategy and lead to bad losses. So there's different types of adversaries. There's adaptive adversaries, which take the player's previous actions into account, and there's oblivious adversaries that set the loss values in advance, or in any case, independent of the actions of the player. So if we think of a small investor in stocks, then he might reasonably think that his own actions are not affecting the prices, but a major investor his actions do influence the prices. Okay, and the basic feedback models, the two most basic ones are, well, the bandit feedback model I'll talk about today, where the player only sees the loss resulting from his choice. He doesn't know what would be the loss had he done something else. But there's also the full feedback model, which is sometimes reasonable, where he says he knows after the fact what would have happened had he made another choice. So there are many examples of this type of problem. So one which Ofer particularly likes and is featured here is relevant to display of news articles in an automated news feed. And one has to choose which ones to display at every time to maximize the clicks. And another one is that I mentioned is obviously the choice of stock investments. So the setting will be a T-round game between a player that can randomize, and here we can think of a deterministic but possibly adaptive adversary. You can also randomize the adversary. So the player has one of k actions. Think of k equals 2 for most of the discussion. Before the game, the adversary chooses a sequence of loss functions. And in the game, for every time, the player chooses a distribution over actions and draws one from that. And he suffers and observes also his own loss, which is the function determined initially of his actions. Now, in the most classical setting, his loss is just a function of his current action. But we're going to consider also a function of past actions as well. Now, if the situation is full feedback, then the player observes at every time what would be his loss if, not just for his own current action, but with different actions currently combined with his past actions in the past. So again, the classical case is when ft don't depend on x1 to xt minus 1, but just on the current action. And then it's just you observe all the possible losses in this stage. So obviously, adaptive is a much more dangerous classes of adversaries. And so the player's cumulative loss is what he wants to minimize, but he's going to compare it to a benchmark. So the player's regret, well, one kind of non-trivial aspect when people enter this field is what's the right benchmark? Because you could think, well, maybe the right benchmark is the optimal choice of action at every step, but that's kind of an impossible benchmark. So more realistic and still challenging benchmark is the best constant action. So think of these not necessarily just as different stocks to pick every day, but also maybe it could be a collection of experts. Each one advises you what to pick every day. So, and each time you go with one of the experts and follow his advice. And there are a bunch of experts, and what you want, but before the game, you don't know which one really knows what he's talking about, which is a real expert and which is a fake expert. So what you want to do is to do as well or almost as well as the best expert. So this is so this means almost as well as the consistent choice of the same action every step. So this is this definition of regret. So we compare the cumulative loss to the minimum over all choices of actions of just repeatedly using this action all the time. So since this is loss, the best is the minimum. And what are called no regret, or should be called sublinear regret algorithms, are algorithms that assure that the regret is negligible asymptotically compared to time. So this means that the player must be getting better over time and really learning from his experience, because initially when he knows nothing, he will, in this setup, get kind of a constant order 1 regret every step. But if he can eventually get it to be sublinear, that's a sign of learning. But then there are refinements of this. So it turns out that you can never get better than order square root of t. So this is kind of the best regret we would want to achieve. And that's easy to see. I'll come back to this point. Just if the environment is just independent and random, you're going to incur this loss of root t no matter what you do. But regret of root t is pretty good in t steps. The other extreme is when you can't get sublinear regret. So the regret is order t, and then the problem is unlearnable. And this is so R of t was defined for a particular algorithm. R star of t is the best over all algorithm, all randomized player strategies. So there's so it's inf over player strategies, and then sup over adversary loss sequences of the resulting expected regret. So one thing which is well developed are algorithms that achieve good regret bounds. And there are several: follow the leader, follow the perturbed leader, and maybe the most famous is the multiplicative weights algorithm, which is very simple. And there's prehistory going back before these papers, but the basic idea of the algorithm is each time we see the losses of the different actions, and we reweight them by according to their loss. So we punish an option that had a big loss by a factor e to the minus gamma times that loss. So a good case to think about is when the losses are just zeros and ones. That's already a rich case, just pure 0, 1. In that case, so every option, either you lost nothing or you lost a unit. And in that case, what the algorithm says, well, if an action lost your unit, then, or if an expert lost a unit, then you give that expert a lower weight by a factor e to the minus gamma. And in general, e to the minus gamma times the loss. And so each time you adapt the weights, you adjust the weights this way. So at time after t minus 1 steps, every expert has a weight which is proportional to this expression, right? So you sum the losses of that expert, multiply by minus gamma, and exponentiate. So these give you weights. You normalize them to a probability distribution, and you choose your next action according to this normalized probability. So mu t is just the normalization of this expression. And you can calculate, or you can estimate what is the regret of such an algorithm. And it turns out that if you know the horizon is capital T, the optimal gamma is of order 1 over root t, and it yields a regret of order root t log k. Now, note this: to implement this algorithm, we need to be in the full feedback model, because I have to know for each expert or for each action what is the cumulative losses until now in order to calculate these factors. So in the full feedback model, I can calculate this, and then it turns out this classical result that the regret scales like root of the time, and there's a dependence, logarithmic dependence on the number of actions. Okay. Now, perhaps surprisingly, in the case of a small number of actions, you can do as well with bandit feedback. And I still find this surprising. This was found more than 10 years ago. What you do is you apply the same multiplicative weights algorithm with the actual losses replaced by an unbiased estimator. So every time you, instead of using the loss at time t of action I, which you know only for the action you took, what you do is, for the action you took, you take the loss and you divide by the probability of taking it. So this is a number you know, and of course the probability you know because that's been calculated from the previous step. And all the actions you don't all the actions you haven't taken, you just give them weight 0. So this LT hat is replacing LT, and you can see if you take expectation of this with respect to mu t, you get back to the vector LT that we were looking at before. So this is an unbiased estimator of the true loss vector, but it looks a little strange, right? We were supposed to take the vector of the losses, and we're taking a vector which is has a single non-zero entry, which is rather larger than the loss because we're dividing by a probability that could be small, and all the other entries are 0. And kind of amazingly, just plugging in this and running through the proof, it works. So as I said, the proof of this is not hard, but I still find it surprising.
Is the scaling square root k tight?
Yes, the scaling is tight. So that's a change from, so when you have more and more actions, then there is a cost to the fact that you're not seeing the different weights. So this is tight. And right, but I'm going to focus on small number of actions where the difference between the root k and the root log k is not important. But when you have many actions, yes, this is important. Okay, I'm going to maybe skip some of this and go to the issue of switching costs. So this has been an obstacle that people have noticed for many years in this topic, which is we didn't distinguish the cost for the player of playing the same action as yesterday and switching actions. In many applications, these are really fundamentally different. For instance, in stock, if you have to switch the stock you're holding, there's often transaction cost. In various robotics application, if your robot has several actions that he can be doing, if you have to reconfigure it, there's a cost. And also in these news article applications, there's a cost to switching the action. Nevertheless, Adam Kalai and Santosh Vempala in 2005 showed that an algorithm in the full information feedback, one can still have a regret of order root t, even if you add to it a switching cost. So the setting is we have a new regret expression, which adds so it's the regret from before, the loss at time t, plus a new term which depends on not just your current action, but the last two actions. It's one if you switched actions. Okay, so this is the new form of the loss. And then note that this extra term is not going to cost to our benchmark. So our benchmark was fixing the best action and sticking with it the whole time. So then there is no switching. So this imposes a cost on switching. Nevertheless, they could show a regret of root t by a different kind of algorithm called follow the lazy leader or follow the perturbed leader. So it's a very natural thing to say, well, at every time, let me just choose the action that has done best so far. But this is bad against, in the worst case, adversary, because he would then know what you would do, and he would thwart you in the next step. But it turns out if you each time, if you do a perturbation, so you add to the actual losses some controlled random perturbation, and after the perturbation you choose the best action so far, this turns out to be much harder to thwart, and it works in the full information setting. Even if you impose switching costs, it doesn't switch very often. And I actually talked to Santosh Vempala, and he said, they proved this for the case of full information feedback, and he said he's had on his agenda to prove the same for the bandit feedback, but it hadn't worked out so far. It looked very complicated, and we'll see a good reason for that soon. Okay. Any questions so far?
Maybe a small one. So these codes, they seem to be uniform, so you just switch from any I to any other.
Right. So you could have different.
Parameterize
So if you, right, you could, so one could also vary the cost for switching, and we have some extensions for that. But I want to stick to the simpler setting now. Okay, so maybe there's further feedback models which have been considered, but maybe I'll skip those. And so one can consider longer memory. Here we've considered things of memory 1 and 2. One could extend that. But in the M memory, let's just think of 2 memory. So the switching is an example of that. So let's focus on the top of this diagram. So for bandit feedback and oblivious adversary, we know, so without imposing switching cost, we know root T regret. But what happens with switching? Okay. So let me go on to explain. So our main result is that with switching, the truth is T to the 2/3, which is kind of a new exponent in this subfield. So there was some previous work I'll come to by Cesabianchi, Deckel, and Shamir, but they considered unbounded losses, which really kind of breaks the rules in this kind of model. Okay, so see, there is one. I was hoping that there's no whiteboard to write anything on here. This is no belief in the old style. Okay, so all right. Okay, so let's start with the T to the 2/3 upper bound when you have switching costs, which was well known before and actually is an easy consequence of previous results. So T to the 2/3 can be done just in a black box fashion by blocking. So how does one see the upper bound? You have T rounds, split them into blocks of length B, just equal size blocks of length B. Use this X3, the multiplicative weights algorithm, to choose actions for each block. So we just commit not to switch in the middle of a block. So we think of, so really we make one decision per block. So the number of rounds effectively goes down from T to T over B, because we only make one choice per block. And okay, so let's see what this tells us. What is the regret of such an algorithm if we do the optimal choice, or even just the X3 choice, but only after each block? So what do we know about the number of switches? Maybe we switch after each block, but the worst it could get is T over B, the number of blocks. Okay? Now, the number of rounds we said was T over B, and so we get regret of square root of that. But we have to scale it by B because each action now could cost me B instead of 1, because the loss of a whole block could be as high as B. Okay, so we get this expression. So we write it as T over B plus root TB. And the block size is something we get to choose. So optimizing this sum, we choose beta, which is T to the 1/3, and that will lead to T to the 2/3 here. Okay, both terms equal and give T to the 2/3. All right, so this looks very simple-minded. And the question is, can you do better? The question was, can you do better? And in particular, if for some reason you could prove that the usual X3 algorithm, without blocking, doesn't switch too often, then you could improve this T to the 2/3. Because here we kind of took a worst-case view of the switches. We had T over B rounds, and we said, well, maybe we switch every round. So if you could say, well, the algorithm is not that fickle, then you could get an improved bound. It turns out it can be fickle. So a consequence of our result is that for some adversaries, in order to perform optimally, any algorithm will have to switch very often. Okay, so the question was, what's the correct lower bound? Is it root t or t to the 2/3? And Ofer-Deckel had worked on it for a long time, and he arrived at the conclusion that a more delicate stochastic process was needed, because prior in this theory, the way people got lower bounds was just picking things at random, and in some cases just doing a random walk. So let me go back to the simple case without switching cost. How do you see the lower bound of square root t? So, very simply, both for the online learning and for the bandit, what you could do is just pick the losses IID uniform for the two, say we have two actions, for both actions. And then, so at every step, you really don't benefit much from switching, because both actions will give you the same distribution of loss in the next round. And but the two actions, if we look at their cumulative loss, will get a random walk, a sum of independent random variables. And we know sum of random walk will have some mean and will fluctuate around the mean with a deviation of root t. So one action could deviate up by root t, the other action might deviate down by root t. So the difference between the bottom and the top in expectation is order root t. And I have no way, the player has no way to avoid this kind of regret. So whatever he does, his algorithm will miss some, there's one of the actions will be taken less than t over 2 times, and in those t over 2 times, maybe the action he didn't take outperforms the action he did take, and so that will cause a regret of order root t. But picking things independently at random really it doesn't work as a lower bound for the problem with switching cost, because the adversary, in this case, can just stick, if he sticks to one action, so doesn't switch at all, even if it's the worst action, his regret is still root t. So one needs a different kind of process. So the first, okay, I'll explain this in a moment. So an early idea that was studied by Deckel, Chisholm, Bianchi, and Shamir was to make the losses themselves a random walk. So before we said the partial sums of the losses were random walk, the losses were IID. So they thought, well, if we make the losses themselves a random walk, then, and we're in bandit feedback, so what they thought is we make the losses for the first arm a random walk. For the second arm, it won't be an independent random walk. It will be shifted by some epsilon, okay, up or down. And epsilon will be small. It turns out the optimal epsilon is t to the minus 1/3. So you have a random walk, and you shift it by epsilon up or down. What happens there is that you get no information unless you switch about which is the better arm, because each time to go from the loss at time t to the loss at time t plus 1, what happens is an independent Gaussian, say if it's the steps are Gaussian, independent Gaussian is added. And that's true in both arms, because both arms are evolving the same way. They're just shifted globally by one epsilon up or down. So in order to get information on is this epsilon up or down, which is what you need to know in order to find out the better arm, you really have to switch. So they did this analysis, and it turned out that the regret was indeed t to the 2/3. The problem is that this sequence of losses you get is unbounded, because if you're doing a random walk with steps of order 1, then it gets to be order root t. And the rules of the game are the losses at every step should be bounded. Otherwise, You can cheat. So, so it turns out that this is because somehow the random walk sequence is too deep. So, and what we found is the right approach is to do a kind of, to build the loss sequence by a kind of multi-scale random walk I want to explain next. So the general blueprint will still be, as I said before, so we'll have the losses for one arm will be some stochastic process I'll describe soon. And the other one will be shifted up or down by epsilon. So there'll be a fair coin to toss if to shift the other one up or down by epsilon. And epsilon, the optimal epsilon will turn out to be t to the minus 1/3. Okay, but the way the loss sequence will be constructed will assure that it's bounded. So in reality, what I'll describe here will be bounded by a log t, but log is easily handled. If you just scale things down by log, then you get the loss t to the 2/3 over a log factor. So one thing I've been pushing under the rug is, in fact, we still don't know the truth exactly. We know it up to a log factor. So the kind of processes we'll be considering have the form, maybe it's in the previous slide. Right, so that's written here. So for every time t, we're going to define some parent row of t. So the arrow here points from the parent to the node. So here, say the parent of 4 is 0, the parent of 2 is also 0. And the loss at time t will be the loss at the parent plus an independent standard Gaussian. And it turns, so if the parent function is just t minus 1, you get a random walk. Right? So if each time you add to, if LT was LT minus 1 plus a Gaussian, you'd get a random walk. And the problem is this would grow too fast. If the parent function rho of t was always pointing back to 0, then you would not grow because you just get a sequence of independent choices. But it turns out that then the player can get too much information without switching. So one has to balance these two things. The random walk was ideal in the sense of it gave no information to the player without switching. But it was bad because the losses increased too fast. The independent sequence had the other shortcoming. So here, so this, I'll explain this function. This turns out to be the right choice of the parent function. I'll explain what it is in a moment. So, but just to get the setup, rho of t equals 0. So each vertex, if its parent is all 0, then we just get the independent sequence. And rho of t is t minus 1, which is featured here, just gives us the random walk. So we can define for every parent function its depth and its width. So the depth is how many iterations you have to do till you get to 0 in the worst case. So here it will be order t. That's too deep. And the depth means that the total losses will grow out of bounds. The width of the parent function represents, if I look at some intermediate point and ask how many of these edges cross over it. And I also don't like large widths, so I want the widths also to be polynomial. I'm sorry, logarithmic, not to be linear or polynomial. So why is width bad? So the problem with width is if I have some time, time 100 and have many arrows going over 100, what does that mean? It means that if I switch at time 100, there'll be lots of observations for me where I can compare two variables and their difference is either a Gaussian or a Gaussian with a perturbation of epsilon. And I can use all of these to test whether the perturbation is up or down. In this random walk example, if I switch here, then I can only compare the step 1 to the past and 1 from the future. And that's really the only information I have. due to this switch. So if you have a Gaussian and a Gaussian perturbed by epsilon, the information content of that is epsilon squared. So you'll need 1 over epsilon squared such switches before you can tell if the perturbation was up or down. But if the function is very wide, like in the ID case, then by just switching, you get a lot more information. So you can kind of average the observations before the switch and after, and that will really zero down on the epsilon. And you can do that without many switches. So what is the function here, rho of t? So it's written this way, but it's better to think of it in binary notation. So given every t, write it in binary, and look at the least significant one in binary and erase it. That's rho of t. Okay, so if t, I don't know, if t was 6, 1, 1, 0, then rho of t will be 4, 1, 0, 0. So just erase the least significant one. So in particular, you see that, let's go back. Right, so this is part of this picture, right? So all powers of 2, their parent is 0, because you erase there's only one single bit, which is 1. You erase that, you get back to 0. So all powers of 2 point to 0, but here 6, its parent was 4, and so on. This is the function. And if you think about this function, it really has both height and width, which are logarithmic. So from every integer, the height is just how many times you can erase 1s until you get back to 0. Well, they're only logarithmic number of digits. So obviously the height is logarithmic, and it's also not hard to see that the width of this function above every point is just logarithmic. And that turns out to be key. So the actual analysis is based on chain rule for relative entropy and Pinsker's inequality relating total variation to entropy. And let's see. Okay, so this is explaining how these two loss sequences behave. But what in the end we get is an inequality in total variation that says the difference between doing if I haven't done enough switches, so if I've done less than t to the 2/3 switches, then I can't tell between if the second arm was moved up or down by epsilon. That's the conclusion of the technical analysis. So we really bound the total variation distance by in terms of the square root of the number of switches. So and really create this dichotomy. So either you make at least t to the 2/3 switches. If you do, then that's enough to tell if you switched up or down by epsilon. But making so many switches already costs you t to the 2/3. If you do less than t to the 2/3 switches, you don't have enough information to distinguish between the arms, if the second arm was switched up or down. And so whatever you do, you have a constant probability to just play too many steps on the wrong arm. And if you do, every time you go to the wrong arm, it's epsilon below the other. Note it's crucial here that we have bandit feedback. We never get to examine because if we got even one time to examine the two possible losses, we see, oh, one is epsilon higher than the other, and the game is over. But every time we only see the loss from one of the actions. And so if we can't distinguish the arms, then we're going to make a constant fraction of mistakes in expectation. And so we'll pay epsilon, a payment of epsilon, order t times. So that will give us epsilon t. And because I said we'll take epsilon t to the -3rd, we'll get a cost of t to the 2/3 in this case. So, damned if we do and damned if, or for the player, if he does many switches, he will know the truth, but he's already paid too much for this knowledge. And if he doesn't do enough switches, he doesn't pay much, but his ignorance costs him. Okay, so that's said. To determine a Gaussian with accuracy epsilon, you need 1 over epsilon squared switches. And if it has standard deviation sigma, you need sigma over epsilon squared switches. So the whole point is that this low height of this process allows us to choose sigma, which is essentially order 1 or like 1 over log t, because after all, if you want the losses to remain bounded, you have to take into account that you're summing Gaussians here. So you don't want to sum too many, but because here the number of summons is at most logarithmic, then if you make the sigma 1 over log t, then you're still okay. While in the random walk example, in order to, if you wanted to keep the losses bounded, you'd have to make the sigma so small that the number of samples you'd need to differentiate would not be so big. Okay, so this repeats some of the points I mentioned. So the width is the maximum size of any vertical cut in this graph. And a switch contributes at most width row samples where I can see a variable which is a Gaussian plus or minus epsilon. So that's why I needed to control the width. And on the other hand, because we want the loss to remain bounded, we have to set sigma, which is like 1 over the depth. And we want the depth to be small so that this sigma is not too small. So again, repeating, each width gives at most width row samples. The loss is bounded in 0, 1, so we'll take the variance to be order 1 over depth. And the conclusion is that the number of switches needed to determine the better action will be t to the 2/3 over this product. So if you make fewer switches, you just can't tell. And of course, if you make so many switches, you've already paid this cost. Because the width and the depth are logarithmic, you pay essentially t to the 2/3. So I said this function has both depth and width, which are logarithmic. Okay, so we now know that bandit and switching are hard in the sense of this t to the 2/3, and so one can reduce some other models to these and deduce that they are also hard. Maybe I'll skip that. Let me just say what is the dependence on k. So if I focus on the case of 2 arms or 2 actions, but if you have more actions, we can also analyze it and see that the dependence is now k to the 1/3 on the number of arms. So similar ideas. And this paper will appear in Stock, and it's available on the archive if you want to see the actual details of the proof and the dependence on the number of arms. Okay, thank you for your attention.
If I see both costs every now and then I should be able to break the lower bound because I see.
No, what it says is if for the particular adversary we constructed, if you see it even once, yeah, it will be different.
Is it clear that this is tied to? I mean, for this strategy, it's clear. It's sort of intuitive why. But are there algorithms which could actually take advantage of sort of a small amount of extra information to do better?
So you're saying, suppose the algorithm got to see in a few times.
Yeah.
Right. So the question is, are these times known in advance also to the adversary or not?
I guess not, because otherwise it would hide.
Yes. So that's actually an interesting variant. And are these times chosen at random or chosen by the player? Right. We could think of both models. So maybe the player has a small budget of times where he can somehow pay off someone and get information on the losses of the other actions. Or it could be that these are rare random events that suddenly he sees the results of the other actions. So that's actually an interesting variant. We haven't thought of that. But it reminds me of this book reviews in Amazon Canada. You know this story? So people submit reviews of books, and the reviews are under pseudonyms, but Amazon insists that people send their real names and emails in order that are verified in order for these reviews to be published. but then they're published under pseudonym, so nobody sees them. However, there was some glitch in Amazon Canada a couple of years ago, where suddenly all the real names appeared under reviews, and suddenly it became clear that many of the exceedingly positive reviews of books were by the authors themselves. So, so an unexpected glimpse into information you were not supposed to have can be quite interesting, yes.
Any other maybe a small question. So the use of multi-scale random walks, so to prove a lower bound in your case, how standard it is, like for showing lower bounds in general?
Well, certainly, I think it's a new idea in this setting. This type of random walks, my co-author John and I and many others have studied them in probability for other reasons. So let me give, without proof, just another way one can obtain this type of multi-scale walk. So start with a binary tree and label it with Gaussian variables. And this corresponds to a branching random walk. So you think of a particle that splits, and each time the two children move independently Gaussian, and they split, and so on. So these branching random walks have been studied for decades, and a lot is known about them. So this creates this tree structure. Now, suppose you take this tree and you do a depth-first search on the tree, each time recording the sum of the variables from the root to where you are. So now you'll get a sequence of variables, and it turns out this is exactly this multi-scale random walk in another alternative description. And this is something that has been looked at in the probability literature for other reasons. We're interested in how the branching random walk behaves. So along every path of the tree, you just have a random walk, so we know how that behaves. But you have a big collection of correlated random walks, so they're interesting to study, how the maxima and so on. So this is a process we've studied a lot, so kind of it was something on our mind when we heard the question.
All right, so we could conclude that. Otherwise, you can speak to Yuval offline, so please let's speak.